All right, it's my pleasure to introduce Henry Adams, who's at Colorado State University. And yeah, Henry, thank you for joining us today. Please take it away. If you could share your screen, please.
Oh, thanks for the reminder. I forgot. Yes, thank you, James. And I'd also like to thank Lenore and the other organizers for giving me the chance to speak. And I'd like to thank all the audience members for joining today as well. So I want to give, I maybe have two goals for this talk. I want to give an introduction to applied and computational topology, which is my area of training and where I've been working for a long time. And then I also wanted to give you an introduction to this particular new data application that I'm looking at coming from chemistry. So I'm assuming we have folks from all different types of data science here, which is wonderful. I'll give a nice slow introduction, hopefully, and please interrupt me with questions as we go. So the title of my talk is Descriptors of Energy Landscapes Using Topological Analysis. It's also the name of a recent grant that I'm part of, mostly with chemists, just a couple of mathematicians, of which I include myself. I'm in the math department. So here are the folks on our team. So the only other mathematician is at Boulder, right nearby me. But we have chemists at Washington State University in Auburn and Arkansas, and at Illinois and RPI, we have sort of physicists who work a lot with chemistry data. My teammates all met each other at an NSF Harnessing the Data Revolution week-long mixer, where they tried to find people to work on interdisciplinary problems together. And they added me on afterwards to join in. But the point is really to understand energy landscapes of chemistry molecules from a mathematical perspective, and then to provide descriptors of those molecules for use in machine learning tasks, for example. And in particular, we're looking at descriptors coming from topology and geometry. So I'm not a chemist, but let me do my best to describe a little bit of chemistry for you. What is often done when you're given an energy landscape to describe the configurations of a molecule is to describe it using a merge tree. So down on the bottom left, I have a merge tree. Okay, so pretend on the top left, this is the energy landscape for a molecule. I'm lying, I just made that in MATLAB, okay? But pretend that is the energy landscape for a molecule. You know, each point in our 2D domain is encoding a different configuration of the molecule, and then the function height is the energy of that molecule. And when you find the molecule in nature, you know, you'll frequently find it at the global minimum, but you'll also find it at various local minimum. And chemists are very interested in things like, you know, what's the minimum energy path from one minimum to another? What's the barrier of energy that you have to inject into the system to move from one configuration to another? So the merge tree, of course, gives you a lot of information about the landscape, but certainly not complete information. The merge tree is just tracking the connected components of the energy landscape. These two energy landscapes at the top, A and B, they have the exact same merge tree. So both A and B have the merge tree as drawn on the bottom left. But some of the connected components in example B really have this Swiss cheese-like behavior. Okay, some of the connected components in the energy landscape B have holes in them, and the merge tree is completely ignoring those holes. It's only keeping track of connected components, not holes as well. Questions so far? We're going to be looking at something called persistent homology, which I'll introduce, which can also track holes. So the one-dimensional bars in persistent homology are going to track holes. In blue, I've drawn the one-dimensional bars. The zero-dimensional bars are just going to track connected components. So there's sort of this dictionary between the zero-dimensional bars and the merge tree, right? So these 4 bars correspond to these 4 parts of the merge tree. These 4 bars correspond to these 4 parts of the merge tree. right? So there's a nice correspondence between one-dimensional persistent homology bars and the merge tree. The nice thing about persistent homology is that you can also track higher dimensional features like these one-dimensional holes. Okay, and once we have these bars that encode more of the geometry, our future goal after that is to do machine learning tasks, potentially using these barcode descriptors. All right, so let me give a little bit of a background on homology and persistent homology. So the I-dimensional homology group, HI, and this is all roughly speaking. Roughly speaking, what it does is it counts the number of I-dimensional holes in a space. Okay, so when you do homology with coefficients in a field, you get a vector space. The rank of the vector space is what counts the number of holes in each dimension. And because it's linear algebra, to compute homology is really just Gaussian elimination. You can code up homology algorithms quite efficiently on computers. So H0 is just the number of connected components. So connected components are zero-dimensional holes. So that first example in the top left has 6 connected components, whereas my other examples all have 1 connected component. Okay. H1 counts the number of one-dimensional holes or loops. The first example has no loops. The second example has 3 loops, going around the pentagon, the triangle, and the other triangle. The sphere has no interesting loops, just because any loop that you try to draw on the sphere can be contracted down to a point. And the torus has 2 interesting loops. So you can go around this way. You can go around this way. There are other loops you could draw on this torus, say wrapping around once in each direction, but that's a linear combination of the other 2. And then you can also talk about 2-dimensional holes. So the sphere, this is a hollow sphere. It has a single 2-dimensional hole. You can fill it with jelly and the jelly won't spill out is the interpretation. And the torus, this hollow torus, also has a 2-dimensional hole. Again, you can fill it with jelly and the jelly doesn't come out. Questions on homology? All right. Persistent homology is a way to apply homology not to a single space, but to a growing sequence of spaces. Here, you can see how my spaces are growing. I'm including more and more of my torus. At the end of the talk, I'll talk about a common way in which people obtain growing spaces. Namely, you have a data set. It's perhaps sampled from a manifold. So you have 1 million points sampled from a manifold. Well, the shape of the data set is just 1 million discrete points. But we're going to thicken the data set by growing balls around the data set. And then as you grow these balls, you get growing spaces that do a good job at estimating the homology of the unknown underlying manifold. That being said, the first part of my talk will be on sublevel set persistent homology. So what we have here is a space. For us, it's a torus right now, and it's equipped with a map to the real line. So, we have some space and we have a map to the real line. It doesn't need to be a manifold, our space. And we're sort of cutting our space at different heights and looking at the regions below that height. So if I cut my torus at 4 heights, I get these 4 different pieces. And sort of the bars beneath track how the holes are changing. So this first slice is just a disk. I guess it's a bowl, but it's really just a disk. And it has a single connected component and no other holes. So that's why it intersects 1 bar in dimension 0. because it has one connected component, but no bars in higher dimensions. This next slice is a macaroni noodle, right? It's the same shape as a circle if you're allowed to shrink it down. So it has a single connected component and one loop in it. This next slice, you could actually shrink this down to a figure 8, and it'll have 2 one-dimensional holes, still a connected component. And then finally, our last slice has a 2-dimensional hole as well. So persistent homology is tracking the number of holes as a space is growing. It's fast to compute as well. So I want to give another example of this sublevel set persistent homology on a chemistry example. So we're going to look at the n-alkanes. I lost my hydrogens. Okay, here are my carbons. And let me put 5 carbons in a string. Okay, so here are my 5 carbons. The carbons are all connected in a line segment. All of the interior carbons also have 2 hydrogens sticking off of them in blue. And the hydrogens, really, they play the role of fixing this angle between adjacent carbons, because all the atoms around this carbon want to arrange themselves in an energy minimizing way, sort of around a tetrahedron. And so the hydrogens play the role of fixing this angle between adjacent carbons. The carbons on the ends have 3 hydrogens sticking off of them. Okay, so one way to describe this molecule would be X, Y, and Z coordinates for each atom, okay? And other folks on my team are doing actually dimensionality reduction techniques to try to take high dimensional representations of molecules and reduce them down to better collective variable representations. So you don't want to encode these 5 carbons in 15-dimensional space using 5x, 5y, and 5z coordinates. A better lower dimensional description is using 2 dihedral angles. So this bond can rotate right here. That's 1 degree of freedom, 1 dihedral angle, and we have this other degree of freedom, okay? So we're gonna think of this energy function drawn on the right as a function on the torus. It has periodic boundary conditions. All right, so we're going to compute the sublevel set persistent homology, and we're going to get these bars tracking the 0 and the 1 and the 2-dimensional holes as we look at the sublevel sets.
Henry, so it's a sublevel set of what domain?
Yeah, so the torus is the domain and the function is the energy. So we have this torus, right? And then we have an energy function, which is what's drawn in the blue, green, and yellow.
And that was computed like experimentally or something?
So this particular example drawn here is, well, let me jump ahead a bit. First, I'm going to do the really the easiest case where we have an analytical description of the energy landscape. Okay. So we're first considering the energy landscape where we don't pay attention to interactions between non-bonded atoms. Okay, so dihedral angles have energies associated with them, but there's also an energy associated between this first and this 5th carbon, right? If they get super close, that's high energy, right? So at first we're ignoring that, which is going to make the problem quite mathematical, quite combinatorial. Then we're going to add back in that interaction between non-bonded atoms, and then it will no longer be a analytical energy landscape, but it'll be a numerically sampled one. Okay. So some of my colleagues are doing, the chemists are doing molecular dynamics simulations, you know, so this is on the right, we have the analytical energy landscape, but on the left, you know, this is what you get out of molecular dynamic simulations. You get a bunch of points in the domain and a bunch of associated energy values. And
so they're just running a simulation at every time step recording the location?
That's right. They, you know, it's like um, they're letting the molecule evolve according to energy, and they're tracking the configuration of the molecule and its energy at each point in time. Then, if you have good collective variables, in this case, the dihedral angles, you know, then you can plot all these points in the lower dimensional space. Your lower dimensional space representation is on the two horizontal coordinates in this picture, and the vertical axis is the associated energy.
Very cool.
So once we get to this data on the left, a further step will be sort of like smoothing the sampling from the function into a complete description of the function. Right now, I'm working with the complete description of the function. In fact, I'm working with the function that's not taking into account interactions between non-bonded. So it's a simple function at first. Other questions? All right. So the first time through this, I just want you to look at the sublevel sets on the left. So I'm going to show you increasing sublevel sets on the left. We're sort of raising the water level or the energy barrier and including more and more of the domain that allows for higher and higher energy. So on the left, we see this sublevel set that just hits the first global min, and then 4 local minima appear. 4 more local minima appear for a total of 9 connected components. Some of the local minima start to merge. So now we have a path between these minima that's beneath our set energy barrier at this stage. And then the minima connect up again to form holes. Remember, we're on a torus, so the top is identified with the bottom. So what's going on in this next slide is that the connector between the top and the bottom appears. And then more bridges between the top and the bottom appear. Some holes fill in. And then finally we get to the entire torus. All right, so we just swept this energy function on the right side. Let me do it again, but talk you through the persistent homology barcodes as well. All right, so H0 is in red, H1 is in blue, and 2-dimensional homology, which only comes once the entire torus is there, will appear in green. So right now we just have a single connected component. We get up to 5 connected components, and then finally up to 9. Okay, at the next transition, we have these merging events. So the 4 connected components that were born at this energy level have now died. They've merged with an older connected component, the global min. And at this stage, I now have a single connected component, and I have 4 one-dimensional holes. So those one-dimensional holes are tracking these right here. When I get this bridge from the top to the bottom and to the right and to the left, each of those give me 2 more holes. So now I have 6 holes in total. All right. I get more bridges, so I get more holes. I guess I have 10 one-dimensional holes in total. 4 of those holes have filled in, right? These 4 holes that you see there, most obviously, they get filled in. So that's why these 4 one-dimensional holes have died. And then as the bridges merge together, more of these one-dimensional holes fill in. And then finally, once you get to the very end, you just have the homology of the entire domain, right? So the torus had 1 connected component, 2 one-dimensional holes, and 1 2-dimensional hole. Questions about the correspondence between these bars and these sublevel sets? All right, so the point is that all this was the merge tree. It's really encoding the information from the merge tree. But we are also tracking, you know, the Swiss cheese-like behavior of the energy landscape of this admittedly simple molecule. You know, the Swiss cheese-like behavior is encoding things like how many minimal energy paths do you have? Here might be a minimum of energy minimum number 1. Here might be another minimum of energy. That hole is sort of saying how that we have 2 minimal energy paths from one configuration to another. So you shouldn't expect to be able to write down a single way that this molecule evolves from the one minimum to another. It's really many such paths are equally good. That's one piece of information carried by the one-dimensional holes. Okay. So let me try to convince you that this is computational as follows. I'm going to start with butane. So only 4 carbons. And then we're going to keep adding carbons. And we're going to get higher and higher dimensional functions. So right now, this is just our energy function from the circle to the real line, because we only have 1 dihedral angle. So for butane with only 4 carbons, there's really 1 degree of freedom. But more generally, we're going to get this function from an n-dimensional torus to the real line, where n is the number of these interior dihedral angles. Okay, so we're going to start with 4 carbons, but add them one by one. Okay, so this is butane, 4 carbons. This is an energy function on the circle drawn on the right. So here I have energy and dihedral angle. And if I call this height alpha, that's the birth of the global min. If this height is beta, that's the height of these 2 local minima. And then if this is gamma, that's the death of those local minima. So I'm back up to 1 connected component in the sublevel set. And then once I get to delta, then I get the full circle in my sublevel set. And the circle has 1 connected component and one-dimensional hole. Questions? You can almost try to visualize these red bars, these 0-dimensional connected components as living on this energy landscape. So that was the case n equals 1 dihedral angle, 4 carbons. We already saw n equals 2, so 2 dihedral angles and 5 carbons. But you can also compute this for the energy function on 3D. So this is an energy function defined on a 3D torus. We have hexane, which has 6 carbons and 3 internal angles. So you're seeing not only H0 and H1, but also a lot of interesting H2, 2-dimensional holes. Let's go to heptane. So heptane has 7 carbons and 4 internal angles. So this is now an energy function on the 4-dimensional space, the 4D torus. Humans aren't equipped to visualize such functions, right? How are you going to visualize a function on 4D space? But we can still compute 0-dimensional holes, 1-dimensional holes, 2-dimensional holes, 3-dimensional holes, etc. Octane, 8 carbons, the 5D torus, and the final one we try to compute, still just on a laptop, is nonane, so 9 carbons, and this is a 6-dimensional domain for our energy function. So
and,
6 to 8.
If I ask a question, so your landscape is still coming from an analytical solution?
Yes, this is all very analytical.
Okay.
Yeah, we'll be able to compute these even when it's not analytical, but we won't be able to get a mathematical characterization. So we computed these, and then we started noticing patterns in all the bars, and then we made a guess. This is a really analytical, simple energy landscape, not taking into account interactions between non-bonded atoms. Let's try to mathematically describe it. We were able to give a proof of in this analytical case, the bars for any number of carbons. I like when applied math and pure math really coincide and interesting questions come out of applied math that you're able to analyze and inspire the development of new mathematics. So to do this, we really end up using a Kuhneth formula for persistent homology. Kuhneth formula is, maybe if you took graduate topology, are a way to talk about the homology of product spaces. And there's a Kuhneth formula very recently developed in the last couple of years, not only for homology, but also persistent homology. And that's what we use here. In some sense, you take two persistent homology barcodes for butane, and you multiply them together to get the persistent homology for pentane. Let me go to the non-analytical case, which is a good point. James has been raising. So, okay. So this is the analytical energy landscape. This is the maybe the real energy landscape. So I think I drew the wrong picture before. I drew the real energy landscape, even though I was using analytical before, just because it's a prettier picture. So the one on the left is where we're not taking into account interactions between non-bonded atoms. The one on the right, we are taking those into account. So the barcodes on the left, these are the ones that we were able to prove what the barcodes are for all alkanes, no matter how many carbons you add. The ones on the right, you'll have to compute more carefully. You won't be able to give a mathematical proof. You'll only be able to rely on your computational experiments. And I don't have pictures of those. We're 8 months into our grant, so still a lot of work to be done. There are notions of distances between bars. It's not always easy to come up with notions of distances between energy landscapes. If they have the same domain, sure, but I guess you could do the L infinity or the L2 notion of distances between functions. But you could also look at notions of distances between barcodes. And so we're happy to see that many of the phenomena are preserved in the simple energy landscape to the more complicated one, especially at lower energies, which is what people care more about. But certainly not everything is preserved. So here, this is on hexane. So and this is sort of the analytical. So even though we can't mathematically prove the barcodes for the real energy landscapes, we can still mathematically compute them. And there's some correspondence. Let me try to describe some of the interesting chemistry that we might try to explore, though I'm not a chemist. So there's an odd-even effect in the alkanes, meaning as I go from an odd number of carbons to an even number of carbons, you see an odd-even effect in things like the melting point or the boiling point. So I guess the boiling point does not have this odd-even effect. So this is the number of carbons. And on the vertical axis, this is something like temperature. So boiling point, there's not an odd-even effect. As I increase the number of carbons, the boiling point is going up. However, for melting point, there's this odd-even effect, this zigzag behavior. The melting point goes up and down with the number of carbons. For some stages of matter, I forget it's for gas or for solid, maybe it's for solid, these odd even effects have been explained partially by packing phenomenon, okay? So, this is, let's see. I'm not sure which is odd and which is even, but in one case, you're able to pack the alkanes much more efficiently if you have an odd number of carbons versus if you have an even. And that's the major explanation that people have for this odd-even effect. Unfortunately, in the liquid stage, things aren't packed, right? In the solid stage, they're packed, but in the liquid stage, they're not. So this is a pie in the sky goal. potentially could we relate things like these one-dimensional holes, the number of paths you have between different low energy configurations to these odd even effects. I think it's it's not clear at all that homology has anything to do with that, but it's nice to have these questions in the back of your mind when you're trying out new tools. The broader goal of the Delta grant is to find descriptors of energy landscapes so that we can predict how chemical systems are going to behave. For example, if you change the pressure, if you change the salinity. And so you want to potentially look at machine learning predictive algorithms for doing this. So these bars, they're sort of a cottage industry now for taking these bars and turning them into input for machine learning. So I know of about 15 to 20 pages on this topic. I don't do too much in machine learning, but my most cited paper is the only machine learning paper I have, which is on one of the more popular ways of turning bars into input vectors for machine learning. So we're sort of thinking of using persistent homology bars as an intermediate summary of an energy landscape. How do you encode an energy landscape for input into machine learning tasks? Well, that's a little hard, but you can compute these finite bars, which is a more reasonable descriptor that you can plug into energy landscapes. So a task that we plan to do early on is to look at halides. Halides are what you get when you take an alkane and you chop off one of the hydrogens and instead add on a chlorine atom or a bromine or a fluorine. So we want to build training data sets where we create a large collection of halides, and then we give the algorithm some new halide that it hasn't seen before. Maybe these two hydrogens were changed to chlorines instead of others. And then how well can we predict what the energy landscape looks like or the chemical properties of this new halide based on the training we've done on prior halides. Questions?
I mean, so I guess, like, I'm just curious from a chemical standpoint, does it matter which of these things you replace the hydrogen with?
Definitely. Yeah. So, this halide is going to have a different energy landscape than the other one I had shown. I mean, think of it like if it were just a physical system, like a bunch of balls connected with rods. I'm replacing this hydrogen with an atom of much, much larger mass.
Mm-hmm.
Yeah.
Cool.
So a harder energy landscape that's drawn here is, this is an energy landscape that takes into account the hydrogen energies too. So, there's many different levels of complexity that you can build into your energy landscape. I had one that didn't even take into account interactions between non-bonded carbons. Then I looked at one that did. Both of those energy landscapes were still ignoring the effects of the hydrogens, okay? So the hydrogens don't play a large role on the energy, but they play some role. And so, we want to add in more and more layers of complexity to the energy landscape. As you do that, you no longer have the smooth function defined everywhere. You only have the function defined at discrete samples. So I have maybe 12 minutes left, and I just want to describe this briefly. When you have point cloud data, a common thing to do with it to try to learn, say, the homology of the underlying manifold from which it was sampled is to draw balls around each data point. And then as those balls grow, you can track how the homology changes. And if there's a region where you have, stable bars, that might be your guess at the homology of the underlying manifold. So on a computer, instead of storing the union of the balls, you just add edges when balls overlap and triangles when balls have a point of triple intersection. So as I grow the balls, I get these increasing pictures, 1, 2, 3, and 4. 1 is maybe this time where everything's connected, but there's not a one-dimensional hole yet. 2 is at this time where we have 2 one-dimensional holes, a small one and a large one. 3 now is connected with a one-dimensional hole, and then 4 is connected but the hole is filled in. So this is a common way of attacking point cloud data from the perspective of persistent homology. There's a beautiful paper on cyclooctane. So cyclooctane, the oct is for 8 carbons, which I have here. The cyclo means they're no longer arranged in a line, but they're linked up in a circle, okay? Again, I have hydrogen sticking off of each carbon, fixing these angles. There's 2 degrees of freedom here. So there's 2 ways this molecule can bend, but it's no longer a 2-dimensional torus as the domain. The domain is much, much, much more complicated. It's actually, so this is the domain. Each configuration like this is a single point, and what I've drawn here on the right, and nearby configurations are nearby points, okay? So what this space is it's a sphere, as you can see, with a Klein bottle glued inside. What looks like an hourglass is actually a Klein bottle. It's this 2-dimensional non-orientable manifold, and the Klein bottle is attached along 2 circles. So this is a data set not encoding energy information, just the space of possible configurations. And it's already super complicated. It's a sphere with a Klein bottle. You can do this persistent homology on top of this point cloud data set. So I'm sort of growing balls around each of these points. And I find some noise and some more noise. But eventually I find a single connected component, a single one-dimensional hole, and 2 two-dimensional holes, which is the homology of a sphere with a Klein bottle glued inside. The authors have a great sort of map on this Klein bottle and sphere. So in green, I have our sphere. In red and blue, I have the 2 Mobius bands which form the Klein bottle. They've mapped out where some of these common molecule configurations, like the crown configuration, or the chair configuration, or the boat configuration, or the boat chair configuration, they've mapped out where these live on the sphere. Okay, so I guess this is something like a Mercator projection. And the crown configurations appear at the north and the south pole of this Mercator projection on the sphere. These are actually the circles where the Klein bottle is glued on. Okay, so I like this paper a lot. Check it out if you're interested. We next want to do energy landscapes on this molecule. So we want to now define an energy function on this domain. The domain is the sphere with the Klein bottle glued inside, and then do sublevel set persistent homology to understand the energy on this configuration space of molecules as well. So with that, I'll finish. Yeah, it's hard to synchronize languages between chemists and mathematicians, but so far it's been fun and worked out well. And I'm super interested in any questions or thoughts or ideas you all might have. So thanks.
Very interesting. Any questions for Henry?
So you have, like, given like shapes, I think you mentioned this, like have kind of known persistent homologies, and then the goal is just sort of, estimate what the persistent homology barcode looks like and then match that to some known shape to understand it better?
Yeah, that's right. So this is a good example. So let me delve into this a little bit. So okay, so a known shape like this torus, right, has known homology, right? it's not the only shape with those known homologies, okay? So another example shape that has that same homology would be two circles glued along a point to a two sphere, okay? So both the torus and this other shape have the same homologies, right? So homology describes shapes, but it doesn't classify them, okay? And so what we're trying to do with persistent homology is often estimate the homology of a shape. So it's giving you partial data for what your model might be. So now we're in this data context. We don't have the entire torus. We only sample from it. And then we can grow balls around each data point, you know, and track the persistent homology. So what you'll get for this sample is you'll have a lot of connected components, right? But eventually they'll just merge up into one. And then you'll sort of have some noise. You know, you'll have lots of small circles as things are filling in. You'll have some noisy circles, but then eventually you'll converge to, you know, two reasonable circles that eventually fill in. Once the balls get larger and larger, those loops eventually fill in. And then also you'll have, you know, once the union of the balls is a reasonable model for the torus, you'll have this two-dimensional thing. So it's a little bit of an art saying what is the signal and what is the noise, right? But if you get barcodes like this, you'd say, all right, well, early on I had this, these noisy features, artifacts of my sampling, but I might guess that I was sampling from an underlying manifold that had one connected component and you know, these two one-dimensional holes. Oh boy, you know, these two one-dimensional holes and the single two-dimensional hole. So it's sort of a guessing game. I gave a talk earlier this week how this is really the setting in which persistent homology was invented. From a sampling of a shape, can you recover the homology of the shape? And I should say there's theorems along these lines. So you can prove that if your sampling is nice enough, you can recover the homology of the shape. Now, so I predicted in graduate school that applied topology might not like keep becoming more and more popular. It did, not so much for this reason, I would say, but because persistent homology is also a pretty good summary of local geometry. So in a lot of machine learning applications, this noise is being used quite a bit. So pretend you have a flock of birds. You know, there's not some beautiful underlying torus there, but there's a lot of local geometry. Or pretend you have a near hexagonal grid of atoms, right? You did ion bombardment, you get this near hexagonal grid. There's a lot of geometry there. Geometry is not so easy to plug into machine learning algorithms, but part of the popularity of persistent homology now is you can sort of discretize geometry by looking at these bars and then vectorize it to feed those bars into machine learning algorithms. Yeah.
What's like an example of like a sort of machine learning thing? Like how do you vector, like what's the point of like vectorizing, and then what are you trying to predict from those bars? I guess that's a little unclear to me.
Yeah. So let me find some more space. Okay, so all right, so actually here, let me do the following. Yeah, perfect. Okay. All right, so this is an ion bombardment example. So it's a surface and people threw electrons at the surface and the surface decays away. And what's left in white is the atoms, the arrangement of the atoms after you've done this bombardment. So when you do this bombardment, you cause patterns to form. And this is like a hexagonal grid that's nearly perfect, right? And that's what people are trying to synthesize, grids that are nearly perfect, and so they have good conductance properties. Whereas the one on the right, there's a lot of defects, and the one in the middle has some defects. So what if, so your machine learning task might be to predict, you know, the conductance, or, you know, how hexagonal is the lattice. But really think of, you know, maybe you're trying to get a conductive materials, and hexagonal, a perfect hexagonal grid is very conductive. Okay, so you don't want to go look at every such picture yourself, nor do you want to stick wires on either side. You want to teach a computer to recognize ahead of time how conductive is each one going to be. So the prior state of the art was defining geometrical measures by hand. So people would say, okay, typically an atom has 6 neighbors. So this guy, this atom has 6 neighbors. All right. And so I'm going to count that as a regular atom. But sometimes you'll have atoms that have 5 or 7 neighbors, and you'll call that a defect. And so people just did, okay, we'll count the number of defects per unit square, and that'll be one feature. And then we'll, you know, look at all the angles between adjacent atoms, and that'll be another feature. They created their own features, you know, lists and lists of features, you know, to vectorize, to plug into machine learning algorithms. But, you know, persistent homology, if you compute these bars, say these 0-dimensional bars or these 1-dimensional bars, that's encoding much of the local geometry, much of these pairwise distances between nearby atoms. So persistent homology is emerging as a pretty good out-of-the-box summary of local geometry. Don't define 100 local geometry descriptors of your own invention. You know, persistent homology produces a lot of features on its own, is a possible perspective. Yeah.
Gotcha. So like just using this example, like the near perfect one kind of would have like a very kind of standard, nice looking barcode, whereas the defected one, the barcode would be more chaotic, I guess.
Completely. So yeah, in the 0-dimensional bar and the near perfect one, you'd have all these bars that end at exactly the same time, you know, and same for all these loops, right? You're going to get loops that form, right? So you're going to have all these loops that form at exactly the same time. So the authors of this paper, who actually were at Colorado State, which is where I am, they looked at also, they called it the like the H0 variance. So they looked at the variance in the H0 bars, and you know the list of all the H0 bars is a high dimensional vector for use in machine learning that they looked at. But to try to get a single feature that works pretty well, they looked at the H0 variance or the H1 variance, and those alone, you know, are just like single measures that do pretty well. But that's a little bit more this perspective. You know, that's a little bit more defining things by hand, as opposed to giving the machine learning algorithm more than it needs and letting it train on whatever it finds to be most useful. Yeah.
Thank you.
Yeah, great question.
Yeah, great. Any more questions for Henry? Okay, if not, let's thank him again for a very interesting talk.
Thanks so much.
And yeah, okay, so I think we'll be back this time next week. And until then, everyone, take care. Thanks again, Henry.
Appreciate it, James. Thanks, everybody.